Hello. So we are now ready to study how we can handle hypothesis tests. So um, as before, I'm going to consider a null hypothesis of this form. So the parameter theta is the parameter in the model, and we put a restriction on the parameter. So R is a function that you need to know your hypothesis. It is your hypothesis. So what you don't know in the null hypothesis is whether theta satisfies this or not. You don't know theta, but you know the restriction function. And I assume that the restriction is q-dimensional. So you may put, if you put one restriction, then q is 1. If you put two restrictions, q is 2. So q is the number of restrictions in the restrictions. And I will consider the restricted model and the unrestricted model, and then the estimator. So theta hat R is the estimator obtained from your model using the hypothesis as an assumption. So this always satisfies this assumption. But theta hat U is unrestricted. That means it may not satisfy this. So the restricted model always satisfies this equality. So that's the major difference in the estimation. And also, this theory is based on Dewey and McFadden and other textbooks. And Dewey and McFadden has a table of different forms. They classify test statistics in a few number of forms, but the a few is like 13. There are 13 different types of test statistic formulas, but I compressed it a little more, and I'm introducing you 4 different types. So I just deliver the basic idea. The detailed formula may depend on the details of the model. Here, my main purpose is to tell you the idea, how the mathematical intuition, where the test statistic is coming from, and then also you need to understand which test is the most useful and convenient and effective in your setup. So it usually depends on the computational burden. Sometimes restricted model is too complicated to calculate, or sometimes the unrestricted model is too complicated to calculate. So depending on your context, you have to choose one of the 4 types. So let me start. The first type of the test is called Wald test. Maybe the most popular and famous test formula. The idea is simple. The implementation is estimate the unrestricted estimator, and then plug that into the restriction function. And say I will just call R hat. R hat is actually I don't use it. I don't use this notation anyhow. R theta hat is, we are checking whether the R theta hat is 0 or not. And then calculate that and check if this is close to 0 or not. That's it. Most intuitive format. And as long as you can calculate the unrestricted estimator, and as long as you know your restriction, then you can implement this. It's simple. And its test statistic takes a quadratic form. Quadratic form requires the asymptotic variance. Asymptotic variance of R theta hat involves the delta method. So it depends on your functional form, but usually you know the asymptotic distribution of theta hat, and then the asymptotic distribution of R theta hat can be derived by the delta method. So the delta method gives you the asymptotic variance for R theta hat. So this is the estimator for the restriction. And so it's simple, pretty simple. By the way, I put n here because I will show you. So we usually uh, in this case, if you think about this kind of estimator, then the variance, asymptotic variance, I called the asymptotic variance is V, but actually you have to think this as this way. So the variance of theta hat converges to 0 in the end, because as your estimator becomes more accurate as you have more and more data, so obviously the variance will converge to 0 in the limit. So there will be no more randomness, no more error in the limit. So V is a standardized kind. You are stabilizing the variance by multiplying square root n in front of the variance, in front of the estimator. So you have to take it this way. So quadratic form, the quadratic form will be, here you need to have V over n in the place of the variance. So this is the quadratic form. So make sure you have V over n in the variance. And because it is inside inverse and in the denominator, the scalar n can be simply multiplied, and you can erase. You can put it this way. So this is why you have n, or you may think it as square root n should be multiplied to theta hat minus theta 0. It has to be multiplied here and here. So square root n should be multiplied twice. So you have to multiply n. That's the reason why we have n here. And so let's think about the pros and cons of this test. So advantage of using this is that it is general. It is pretty general, and you can apply to this idea. Apply this idea to almost any kind of hypothesis testing. So widely used because idea is simple. And you only need unrestricted estimator. So if the unrestricted estimator is easy to compute, and if you can calculate the asymptotic variance easily from the unrestricted model, then it is good. And so that's what I said here. But the problem here is that you are evaluating the restriction function, but the same restriction can be stated in different forms. For example, these two are basically the same thing. Beta 1 equals to beta 2. So beta 1 equals to beta 2 can be stated in this way, in a linear function, or in this way, as a ratio. The problem of the wild test is that these two have different results. So if you have different results, the reason why they are different is because in the delta method or in the asymptotics, we use Taylor approximation, Taylor expansion. So we only utilize the first order approximation. But if you use a nonlinear function, you are losing some kind of information. There is a approximation error arising from the Taylor expansion. So because of that approximation error from the nonlinearity of restriction function, then depending on the functional form of the restriction function, your asymptotic distribution may be different because of the approximation error. So it is a problem, but in often case, of course, you want to choose the linear function so that the variance calculation is simple. But just to mention, this is a problem. That's the first type of the test statistics. And second idea, Hausmann test. So it is this is proposed by Jerry Hausmann. I think this is a very clever idea. So now think about, before introducing the test, think about this. Theta 0 is the true parameter. And now we are going to compare how the unrestricted model and the restricted model behave. So the unrestricted model converges to the true parameter no matter if H0 is wrong, because the unrestricted model does not use the hypothesis as an assumption. It is always correct. Unrestricted model is always correct. I mean, of course, we assume that the model is correctly specified. We do not think about potentially wrong model. That is not our concern in this chapter. So the unrestricted model is always correct, regardless of the null hypothesis. On the other hand, the restricted model depends on the null hypothesis, because it uses the restricted model uses the null hypothesis as an assumption, as a model assumption. And if the model assumption is wrong, then the restricted model is misspecified. Then it does not converge to the true parameter, and it has a misspecification bias. So therefore, Hausmann uses this idea. So H0 is correct. If the null hypothesis is correct, then both unrestricted model and restricted model converge to the true parameter. Both are true. So they are similar. They must be similar because they are converging to the same point. They must be similar. But if the null hypothesis is wrong, then only the unrestricted estimator converges to the true parameter, but the other does not. So they must be different. Unrestricted and restricted estimators must be different, and the difference is as much as the misspecification bias. So then it's clear we are going to test whether they are similar or not. If you can calculate unrestricted estimator and then also calculate the restricted estimator and take their difference, and if the difference is close to 0, your null hypothesis is likely to be correct. But if the difference is large, then the null hypothesis is likely to be wrong. So that is the idea. Here, suppose that under the null hypothesis, you have this asymptotic distribution, standard asymptotics, and say V hat is consistent for V, then your test statistic takes the same quadratic form. Again, it's another quadratic form, V hat inverse. So the examples of this test includes exogenated test, which I'm going to introduce below. And so simply speaking, exogenated test compares OLS versus two-stage least square or GMM estimator using instruments. And in the panel data literature, if you have heard about this, fixed effects and random effects models are two competing models in panel data analysis. And usually fixed effects is considered robust, but random effect is considered efficient. So they are using different sets of assumptions, and one is using more assumptions. So one is random effect is nested by the fixed effect. So you may apply the Hausmann test idea in here. So Professor Hausmann is a professor at MIT, and I met him before. He's very proud of his idea like this. So he said he's very proud of his idea. Yes, it's a clever idea. And by the way, the main contribution of him is it's not about saying this. It's right. This is important, but I think many people would understand this even before him. But his contribution is coming from this. He he proved that the main problem here is this is very difficult to calculate because we need, so it is easy. We know in most cases we know asymptotic distribution of theta hat u, and we know the asymptotic distribution of theta hat r. But what we don't know is their covariance. So to understand, to calculate the variance of their difference, you need to know their covariance. Uh, that is a bigger problem. How can we handle the covariance? There is no clear theory about that, but Hausmann have simply have a simple answer. The covariance between them equals to variance of restricted estimator, which is quite surprising. And if this is true, the variance between the variance of theta u minus theta r can be written as this. Like, think about this. Like the variance of theta u minus theta r is variance u variance r minus covariance, minus 2 times covariance, but this covariance equals to variance r, and then cancel out in the end the variances variance u minus variance r, which is really nice. Very simple. It's simple. So you only need their respective variance, each of the estimators variance, and covariance is not needed in the end. So it's a great idea. And roughly then, what is the intuition? How could he prove that? You don't need to know the proof, but let me explain the intuition. So first, you need to understand that restricted model uses one more assumption, not one more, uses the hypothesis as an additional assumption. So therefore, the restricted model is more efficient, has a smaller variance, is more accurate. So a variance of the restricted estimator is smaller than the variance of unrestricted estimator. So because of the additional assumption in the null hypothesis, the unrestricted model has additional errors. It has like a larger estimation error, so less efficient. So you may understand the unrestricted estimator. It has an additional error, like on top of the error in the restricted model. So epsilon accounts for the missing assumption in the null hypothesis. So because you do not use the null hypothesis as an assumption, the unrestricted estimator has this much additional estimation error. And now, if you can prove that this additional error is uncorrelated with the restricted estimator, then think about this. Covariance between u and r can be written as covariance r plus epsilon and r, but epsilon is uncorrelated with r. So then it equals to covariance r comma r, which is the variance. So that's basically how the proof goes. So much easier to calculate. It's a really clever result, and he proved it. And then what's good and what's bad? It does not depend on the functional form. So it does not depend on the functional form because what you are utilizing is the estimator, not the functional form. So no matter what the function is, it applies in the same way to both unrestricted and restricted estimators. So does not cause much problem. And of course, it's particularly good if you can calculate both estimators easily. Of course, vice versa. Like if one of them is difficult to calculate, then it's difficult to calculate the Hausmann test. And then the problem here is, I said as if it's so simple, but the problem here is, let me go up here. So we know that this will converge to, I had to write here, it converges to chi-square q. Chi-square q, but so the restriction is the degrees of freedom is chi-square q, but the dimension of theta may be different from q. So then our definition of chi-square does not work here. We need additional mathematical work to do. So in this case, mathematically, the problem here is if q is smaller than k, so theta dimension is k, and the number of restrictions is q. If q is strictly smaller than k, the variance v is not a full rank. The rank of the variance will be only q, and it is not full rank, so the inverse is not taken, cannot be taken. So the variance may not be invariable because of the non-full rank problem. But however, that is a problem in computation or in your work. So, but there is a mathematical way to handle that, like generalized inverse, which will not be considered in this course, but it could be a problem. So later, when you want to implement this, you may see an error in your code when you have a program. So then think about this problem, and maybe you may then your choices. You may study what this is or choose a different test statistic. Okay, I will continue. There are two more test forms, and we'll do them in the next video.